So welcome to Q2 of Milwaukee Tableau user group. If you don't know who we are, the Tableau leadership team for the user group is Brandy Beals, Patrick Lugash, myself, and Josh Connor. Very excited to meet with you. Our mission here is to make sure that we have a place for networking for Tableau, where we can meet like-minded people. Definitely one of my favorite groups to belong to. You get product updates and demos from Tableau or any of the partner vendors, or we get use cases from all of you, our users. So if there's any time when you feel like you need to share your Tableau journey or some kind of new insight of how you're using Tableau, please let us know. We're always welcome and want to hear about it. You'll be able to get new perspectives here. Maybe it's data governance or some other challenge that you're facing, the Tableau blueprint. And we have many wonderful consultants in the area that we partner with and that join our Tableau user group, but sometimes you can get some free consulting from the users. I know that I get information from all of you as well. And most importantly, to hop on the Tableau bandwagon, we definitely want to have fun here. So again, thanks for coming. We are going to do a quick poll. If you've ever been with us before, we try to find out a little bit about you. And then we are going to talk with a very informative and entertaining speaker about what now that we have our modernized architecture and where we have wrapped our arms around our data, what now in terms of analytics. Then we'll go over some tug events and we'll have a giveaway. So for the giveaway, we would like you to ask questions and participate. And that's where we'll pick people to get some of the giveaways, the Tableau swag packages, and we'll also have some gift certificates to the Tableau store. Okay. So we're going to take a quick poll here and find out a little bit about you. So you can go ahead and take a picture of the QR code here. You can also go to this URL and access the poll area.
I just posted the link to the poll in the chat window as well.
Thank you. And Josh, do you want to take it away?
Yeah, and just a little clarification, since I'll be running the swag giveaway later too. So we do it off of audience participation. Generally, when we're in the webinar format, that only happens through the chat window. I would emphasize people to put it in the chat window as the easiest thing. But if we do want to have some open dialogue, or sometimes too, I will keep track of folks. We'll do like a random number sort of thing, and that'll be kind of the order at which we do it. So it without us being kind of live and facilitating with the tickets that we kind of hand out normally, that's kind of the way we do it. So try to get your questions, your comments, questions and comments all in here. And then I'll also keep track of anyone who does it as well, and we'll figure that out. So no worries there, but just a little bit on that. So yeah, Olga, if you want to go ahead and let's give everybody a minute to get this going. I think everybody can do this. You can use your camera, pull it out, use that QR code right there. Click on the link. The link is case sensitive, but if you're clicking on it from the chat, it should be pretty easy. So, and then Olga, if you want to bring it up and run the display for that, I'll walk us through the different questions.
So actually, Olga, you need a slightly different link because you are showing the results. I will send that to you directly, okay?
You got that, Brandy? Okay.
I do. I'm the link queen today. So Olga, you should be able to check the chat window.
Okay.
There you go. Perfect. And you can actually use the buttons in the lower left-hand corner, Olga. The play button in the lower left-hand corner.
There's a little
Left.
gray arrow.
Yep. Here we are.
All right, so a little bit of a rehash from our one, but this will give us some direct quantifiable measures on here. Where are we coming from? So you got the Metro, Milwaukee, Madison, Greater Wisconsin, Midwest, farther still. I'm really interested in the farther stills. If you want to pop that into chat, that would be pretty cool. And it'll qualify you for the swag giveaway. So let us know where you're coming from on some of the far. There we go. Durham, North Carolina. All right. Actually, I'm traveling to the Smoky Mountains this summer. That's going to be my fun activity. So yeah, I mean, given the fact that this is the Milwaukee Tableau user group, we've got a lot of folks from the Milwaukee area, Greater Wisconsin, Midwest. It's really good to see the pandemic has given us a great opportunity to include a lot of folks in a lot of different areas. And then same with our group to participate in other areas as well. So Iowa, I have family from Iowa. So excellent. Well, welcome everybody. Good to see everybody from the different locations connecting together. So you want to go ahead and next one, Olga.
So now in the lower left-hand corner, there's the 2 arrows. Yeah. Okay.
Thank you.
Yeah.
All right. So this one, so recent tool, a little while ago, I think we emphasized it on one of our tugs, but the Tableau blueprint. So yes, you're using it. No, but I plan to, and then no excuses. I gave you the link right there. So it's a free tool, right? So it allows you to get a lay of where you're at, give you some opportunities to take next steps to grow your analytics practice, your community, different areas of where you might need to emphasize or want to grow, help you with leadership discussions, things like that. So it's a really solid tool to help you grow, migrate, maybe more firm up or transform into organization and governance areas as well. So good. Hopefully everybody can stop out there and take a look at that. The blueprint functionality out there, it's really good. So all right, next one. All right, and then just to get a little bit more of like a who's it, what's it out there, like what's your team role? And I pulled a lot of this out of Tableau's specific roles that they do, but we got content authors, pretty data engineers, data scientists. Generally, you'd probably want to split that up, but I didn't want to have so many options on here. But that's more of like your back end type of piece. Data stewards, server site admins. Again, those are probably generally separated, but similar type of area. So nice. The data engineer scientist track is pretty good for the speaker we have today. So that's good. Excellent. And obviously I allowed multi-select because we do all play a lot of different roles here. So this is a good one to just get a feel for who's out in the audience. So, all right, I'll go ahead. All right, this is an interesting one. So would you be interested in instructor-led hands-on Tableau prep and workshop, Tableau workbook workshop? So this is an idea where we are planning for a future upcoming tug, and we want to know what you guys think about the hands-on sort of workshop, and if you've ever participated in those hands-on training exercises where instructor does it, you do it, follow along, ask questions, get your hands in there. Would be more of a standardized data set and then standardized tools that be working with. So this one also is interesting. We'll bring it up later, but we're looking to partner with one of our other Tableau user groups in Phoenix on this one. So more information to come as we get closer to, but we're looking at Q3 for this. Looks like there's a lot of interest. And if you're not interested, you also can participate and watch, right? This is all virtual. So I mean, there's certainly no expectations that you have to jump in and do it and be part of it, or you may not have access to it or something like that. So everybody's still welcome, right? We still want to include everybody in. But this is a bit of a different take, something we're trying slightly different and new, just to see what the group thinks. So thank you guys for that feedback. Appreciate it. All right, the next 3, Phil asked us to include some. So I'm assuming, Phil, do you want us to keep metrics here, or is this something you're recording? I can.
I will be alluding to this throughout the presentation, and these questions might seem a bit out of left field. This is actually going to provide me a little bit of context going in. But it's really just so I have some priors on where everyone's at, and I'm not just repeating things that everyone already knows.
Got it. All right. That one looks split.
Yep.
And then Milwaukee Admirals game.
I'm kind of impressed by the number here, actually. I was expecting a bunch of no's.
I was as well when I saw this come in. I was like, out of the three, that's the one I haven't been to yet. But apparently,
I did refer this to some hockey fans, so maybe they're kind of skewing the distribution here, but this will be a positive. This will make me feel a little bit more confident about the second half of my presentation.
all right. Excellent. So that is the end of our polling. So again, this is just a fun piece of it that we like to do with everybody just to get to know us all, and then, you know, opportunity for presenters to get a little bit to know their audience as well. So thank you all. You know, we will use these for the current meeting, future meetings, all that sort of business. From you know, nice to get to know a bit more about everybody out there. So I'll turn it back over to Olga, and I'll talk to you guys a little later for the swag giveaway. Make sure you guys are jumping in with questions, comments, any of that sort of thing. Keep that coming.
Okay, thank you, Josh. We have the pleasure of having Phil Henrickson at our meeting to talk about data analytics and how the insights that the visualizations in Tableau can bring, and maybe how to foster scientific thinking. And again, now what? We're always looking for that next step. Phil is a data scientist at AE Business Solutions. It was also a professor, I believe in Florida, and I can imagine his talks were very well attended, again, because of the insights and the entertainment. So Phil, I'm going to turn it over to you.
All right, awesome. Yeah, thanks for the introduction, Olga. I'll go ahead and share my screen here. Okay, so thanks again just for having me. I'm very excited. This talk has been in my head for a while. I want to provide everyone with some context before we go in. I gained a little bit of information from you guys regarding the topics. So there's a lot here. The pace is going to be very quick. Do feel free to post questions in the chat. It'll probably be easiest to go Q&A at the end, but there's a lot. So we're just going to jump right into it and get going. So title of the talk, again, now what, with the subtext, model building, science, and analytics. And so really the background of this talk, Olga alluded to it, but I think it's worth kind of mentioning the genesis of this talk, which is a conversation we had with Olga, who remembered a presentation that I gave at a Milwaukee TUG, I think like 2 years ago. And I said at the time, and I think I ended the talk even by saying, so Tableau enables companies to begin their journey of learning from data, the emphasis being on begin. Visualization and reporting are not the end. And Olga remembered this and then eventually was like, okay, I want you to expand upon that. Now, I don't know if she remembered, I also said something else along this line, which is every time I ask a client what they plan to do with a data set and they say, oh, we're going to put it into a dashboard and that'll be it, a part of me dies inside. So as much as this is also me trying to address Olga's question and what does that next step look like, it's also kind of a rant about why I said this. So in general, really what the topic of this talk is about analytics. Our Q2, we want to get to the real stuff. No one seems to get to it. We need more analytics than just visualization and reporting. We want to elaborate on why Phil gets angry when, not angry, more like exasperated when people don't want to do anything more than dashboarding. Getting a dashboard up is great, but what you do with it is better. Do you think that Dr. Phil would be interested? First things, you guys can just call me Phil. I get it. It's funny. I understand. Right. Anyway. To which I essentially said, yes. Can I talk about philosophy of science, astronomy, and/or hockey, particularly minor league hockey? To which Olga said, basically, yeah, sure, why not? I'm not sure why you would, but whatever, go ahead. So if this talk ends up boring you guys to tears and/or confuses the heck out of you, I'm only partly to blame. I'm pulling you down with me, Olga. You're the one that allowed it, so it's not just me. We will share the responsibility for this.
Awesome.
So the talk is really, again, answering this question, the now what. And really that now what comes from this, what do we do that now that we've kind of gotten to this inflection point in our analytics journey in which we have pretty clean data, we're looking at it, how do we learn from it? Now, I think my explanation for this and the kind of, again, the motivation for giving this talk comes from my background. So Olga mentioned that, yes, I'm a data scientist with AE Business Solutions. I've been consulting analytics for about 3 years now. But prior to that, I was a professor at Florida State University, where I completed my PhD in political science, and which, some people go, political science, what do you know about data science or anything? But like in general, my research was on predictive modeling, machine learning, and causal inference, and in a way to study topics like international conflict, political violence, civil war, genocide, good, wholesome topics that everyone wants to study. I'm not going to talk about that today. I will be alluding to some of my other research interests. And just a quick fun fact, I am also obsessed with board games and miniature painting, and this talk very nearly became a board game data talk. I still have that in me. That'll be, we'll punt on that for the future. Now, I work with AE Business Solutions. I'm not going to give you the sales pitch for us, but in general, I'm part of a business intelligence and analytics consulting team. I work as a data scientist to work with clients really at any stage in their analytics journey. For my part, it's at the front end, being able to learn from data via the scientific method, via research experiments, that sort of thing. But we also help really kind of just get you to from where you are to where you want to be, because data is hard, and it's not even that we can help, it's that we want to help. For me, the learning from data is the most satisfying part. It's why I ended up leaving academia for consulting, because the data is rich. There are so many interesting problems that can be solved. And so as part of our team at AE, we've been seeing the same sentiment that Olga expressed amongst our clients more and more, which is we're modernized our data warehouse. We have pretty tidy data. We've built all these dashboards. Now what? We have all this data. What the heck do we do with it? Have we, like, I kind of thought we'd have learned a little bit more by now, maybe. So some clients kind of just think they're done. Like, that's it. We've achieved business intelligence, and that's all that can be done with data. The hearkening to the quote in my mind from this is that everything that can be invented has been invented by the guy from 1899, right? No, there's nothing else out there. We've hit the end of the journey. Other clients kind of just wonder, and even this, like, is this the end of the journey? Well, like, what comes next? Is that all there is, to quote a 1967 song, which I'm sure we were all expecting coming into this? Well, the majority are saying is, given their experience with their data, like, we've starting to discover problems that dashboards, visualizations, reports just simply cannot solve. We need something else. We need something more. And we talk endlessly on my team about the analytics value curve, being given data, how do you achieve value over a sufficient time and process? And really, like, a lot of our clients have gotten to a point of modern business intelligence, meaning we have reporting, we have dashboards, we have visualizations, and we can all go and access this now using tools like Tableau. But the problem is that, well, there's this background belief about how this was going to work. We go from raw data to clean data, we put it into a dashboard, some miracle will happen that will then lead us to find some data-driven insight that will contribute value. And I describe it as a question mark, because this is the fuzzy part. We hope that the data would just ordain an answer for us just by looking at it, and it would be clear and as obvious as truth. But in reality, this isn't quite happening. And so I think a lot of clients are now saying, well, we didn't get necessarily what we need something more. We have these more complex problems. So naturally, we need to move into the world of data science. We need to move into more complex methods. There's a new step in the journey that we need to undertake. And this is good, but there's also a problem with this, because now it's, all right, we have raw data, clean data, into a model, into a dashboard. And now we're looking at the results of a model. And again, we were hoping that this will then lead us to something will just emerge directly from the model. The data will guide us to the answer. We'll get a hashtag AI-driven insight trademark. And so there's a reason that the analytics community has been in a bit of a frenzy over data science, because it purports to offer these answers. You don't have to look that far to find all of the hype around deep learning, machine learning, AI, which I hate calling it that, but people continue to insist. I'm losing that battle. In general, there's a tremendous hype in the analytics community regarding these new advanced analytics and how we can learn from data. And that's okay. And I find this, I'm nodding my head at this, but I'm also a bit worried. And I think we need to have a little bit of a come to Jesus talk about this. we need to ignore this part for a second. So much of our emphasis has been on the data without thinking about the crucial and all important second piece, meaning the science. We need to spend less time talking about data, less time, oh, we built a pipeline, we put it into a model, and now it's spitting out into a dashboard, and we built it, we don't really look at it anymore. We just kind of go with what the model says. We need to think more practically, more concretely about the scientific method and the application of models for the purpose of learning about the world. So this talk is really is an emphasis on science. I think we're all pretty comfortable calling ourselves data people. We hear the term data driven all the time. You know, we have groups motivated around this. This has kind of been a key moniker of the last decade, be more data driven. I don't think we're all comfortable considering ourselves scientists. And I don't think we're even, frankly, as a society right now, we're at a bit of an inflection point between those who have lost their trust in science versus those who do. And I think part of this comes from, for me, a question of should we be striving to be data driven? There's kind of this implicit notion, I think, in the analytics community that yes, we should be. And I would say no. I would argue we should not be data driven. We don't want data to drive us. Data is quite stupid. If we, and this isn't just me saying, I'll appeal to an authority for backup here. Judith Pearl, The Book of Why, research on Bayesian methods, and really an emphasis on causal inference and how we learn from data. And the point of her book is, I hope to convince you that data are profoundly dumb. No machine can derive explanations from raw data. Data can tell you that the people who took a medicine recovered faster than those who did not take it, but they can't tell you why. Over and over again, we see this out in the world, in business and science, and even to some extent in academia. We see situations where mere data isn't enough. The hope, I think, that was implicit, unstated in this desire to be data-driven is that data itself will guide us to the right answers. We will look at the data, some answer will naturally emerge to our question, we will understand something about the world and then be able to make a better decision. Now, this talk isn't about how disastrous that can actually go when you turn over just to let the data steer you in places. I would recommend these 3 books to very much speak directly to the disasters that involve using models without inspecting them and data that is incredibly biased. There's a serious problems that the community of ethics in the data science community is being confronted in how we're making use of models. But more than that, this talk I want to emphasize is like the point that Judith Pearl is making, which is you are smarter than your data. Data does not understand causes and effects. Humans do. And the reason humans do is because we have come up with a method, the method being science. Data isn't it's an ingredient. It's not a recipe. It's not a fully sketched out path to learning. By itself, data offers absolutely no guarantee that you will infer and learn the correct process in the world. Data is, now again, I'm kind of poo-pooing data for a second, but I mean, let's just be clear about its role. Data is necessary for learning and we need to make use of it, but it's not sufficient. Data alone will not necessarily guide us to the right answer. In order to learn from data, we have to use a methodology. Like if we think about what we were supposed to be doing, we were supposed to be looking at what was emerging from the data and gaining some insight into a process in the world that was being measured via the data we have. And then going back and thinking, okay, is this actually working? Is this actually telling us something new that we didn't already know? Is this confirming or disproving our priors? So for all the time we spend working with data, and don't get me wrong, we all we're in this every day. We clean, we wrangle, we prep, we analyze. For all the time we spend working with it, I don't think we spend enough talking about how we actually use data to learn. And that really brings us to the topic of the day, which is building models. And I don't mean just statistical models. I don't mean predictive models. I mean explanations in our head for the phenomena we observe, which we can then often formalize into these models that we build with computers. Now, a good book on this front is from Scott Page, the model thinker. He's an academic, a senior academic at the University of Michigan, social scientist. He said, look, we're seeing a new shift. I think the industry is catching on to this. I'm not the first person to make this point, nor will I be the last. Instead, we are starting to see a rise of model thinking. And the reason for this is simple. Models make us smarter. We are living in a new era in which we have so much data, which can be used to learn so many things about the world, but we just have limited capacity to make use of it. It is difficult for a human to process the quantities of information that we have. By using models, we are able to clarify our assumptions, we're able to think more logically, and we're able to, by speculating about the world and thinking about processes, we are able to think better and then look for evidence that can support or reject our explanations, and in so doing, learn something about the processes we care about. So today we need to talk about models. We need to talk about why we build models from just a basic bare bones perspective. Like, what is the point? Why are we doing all this? Why, when someone says, oh, I'm working on a model of it, why? What's the point? And then I want to actually get into the how do we do this, both from a practical sense of, all right, here's my code, here's what I'm doing. But I mean more from just the general sense of every day when you think about a process, how are you constructing a model to explain what's going on? And then we need to talk about how do we use them once we have them, and how the process is not just a matter of looking at your goodness of fit and then taking it at face value. It is an ongoing, ever iterating process that we need to be more deliberate and more conscious of. So if you're wondering like, oh man, this sounds good, well and good, but we haven't actually gotten any meat of the talk. This is just the intro. Part one of this talk, we're about 40 slides in. We got a lot more to go. Part one, we need to talk about why we build models. Part 1 and 2, we need to talk about how we build models. And then, we need to talk about using models. So there's a lot to get through. I'm going to keep up the pace here. This might get a bit wild. We'll see how we do. To quote a famous mathematician, hold on to your butts. So section 1, building models of the stars and everything else along the way. So Olga mentioned this. In my past life, before I became a consultant, I taught classes on research methods, international conflict, political violence, and civil war. Now, these are pretty disparate, somewhat interlinked, but very disparate topics. And regardless, I began every single class I ever taught with the exact same lecture. So it's kind of fun. I'll actually be able to use some of it so you guys can see what the heck are these professors teaching our undergraduates? What are they learning when they go there? At the very least, if you were in Florida State between the years 2015 to 2018. So this talk that I gave was how to be a social scientist. And the reason I led the talk with this was because I taught classes in the social sciences, which is not, it's a subset of the larger scientific community. But really, I wanted to get them on the same page from the get-go regarding what is exactly that we're doing here. Why are we studying these topics, and how are we studying these topics? So I used Prezi at the time. I'm not going to use it today, so I will spare you all that. But you would zoom around, and that helped keep the Florida State students awake. But this is what the talk ended up looking like. And really, my goal was to address something right away, which is people tend to diss on the social sciences. Mostly, I think, because they have a misunderstanding of what social scientists are up to. Like, even in my own work, I constantly get the, really, you're a political scientist? I don't need to, it's quite frustrating. And don't get me wrong, there's definitely some reasons for this with the replication crisis. But in general, I don't think people understand, like, what does it mean to be a researcher? And so my goal was to say, all right, from the get-go, I'm going to get these students on my side, and I will equip them with exactly what they need to flourish in my class and engage in the enterprise of learning. So I used the coolest possible method I knew to win them over, which was a social sciences textbook from 1975. Now, this textbook is pretty well known. It's an introduction to model building in the social sciences by Laban March. And the reason I assigned it is because it does a great job distilling what exactly are we up to, and why are we building, like, what are we trying to achieve? Chapter 1, what are we up to? And the starting point is that God has chosen to give the easy problems to the physicists. Like, a physicist can build a laboratory and control phenomena. They can do experiments in ways that, frankly, we can't do with people, nor should we, because of ethics. But studying people is hard. But that said, there are some interesting ideas in the social sciences, and Scott Page's book does a good job illustrating this, I think, to the layman. Laban March think that an increase in the quality of our speculation, both in social sciences and in everyday life, would be good. Now, the reason I got into this book, and the reason I want to take us through some of it, is Laban March are really known for their emphasis on speculation. They point out that, look, we are all building models all the time. We constantly are forming our interpretations of the world and then expecting things to take place. But we need to be a bit more deliberate about it. We need to be more consistent in falsifying our models and understanding, are we actually learning? And we really just need to stop and think a bit more than we currently do. So their emphasis was on the fact that speculative models are everywhere, and they're central to how we learn. And we ourselves are constantly doing it. We are forming these partial interpretations of the world to live in it. And on some level, because we don't think about our explanations for why something happens, we don't really think of ourselves as building models. But we are, and we are to some extent all theorists of human behavior. My dissertation advisor once said, like, who among us has not constructed a theory to explain why members of the opposite sex do what they do? We are all trying to guess and think and saying, here's what I think is going to happen. So Laban March, give us basically a guideline for how to build models and how to think about and engage in the process of learning. And one feature in doing that is they frequently ask everyone to stop and think. And I want to let you know that Live and March are serious about this. So you stopping and thinking, this isn't something you can just disregard. But really the best way to learn about building models is to just do it, just jump right in. So I want to give you the first example from their book. And if this was in person, I would be actually like, calling on people and that sort of thing and going full professor mode. Sadly, I cannot do that, maybe sometime in the future. So suppose, for example, we are interested in understanding why some people are friends and not others. Now, this is a great social scientific question. Why do people do what they do? People are funny. They're quite bizarre. Why can we explain why they do what they do? Now, in order to get this and answer this question, we gather some data on a college campus by asking residents of a dorm to give us a list of their friends. It's funny because Live and March kind of take this defensive tone at the beginning that like people think social scientists are weird. And then like first example is, yeah, you're going to go around asking people who their friends are. That's kind of weird, man. There's a reason people are judging you. But anyway, we notice a pattern. Friends tend to live close to each other. They tend to have adjacent dorm rooms. If we look at friendship plots, we see that, hey, they're all pretty close. This becomes an observation that we want to explain. Why might this be the case? We stop and we think. And again, if this was a lecture, I would like literally stop and think for about 15 seconds and ask someone, or we're just going to jump right to it. We got to truck along. One possible explanation is, well, maybe it's just because campus housing lets students choose to live in their dorms. And as a result, people want to live by their friends. So students are just asking to be placed by their friends. And as a result, it's just a selection process. Okay, so this is what this is. I mean, it's just a series of statements, but this is a speculation about the process that produced the outcome we are observing. Friends tend to live closer to each other. This is a model. And what this is we have a basic model of the prior state of the world that we can then use to try to account for what we observe in the current state of the world. It is our speculation about the process that produced what we are observing. Now, the immediately question is this a good model? To which the answer is, well, we gotta find out. We have to ask if this is correct, if our understanding is right, what does it imply? What else should we expect to observe? This is the all-important step that, frankly, I think is overlooked the absolute most. We all speculate, but we don't often say, if I'm right, what could prove me wrong? So if you look at this, you can think about implications, but one jumps right out immediately. It's like, well, okay, this implies that students would have to have known each other prior to the start of the semester, which we could then go check. We could just look at the freshman dorm where they presumably wouldn't know each other, but we notice the exact same pattern. Friends in a freshman dorm tend to also cluster together, which our process can't explain. Our process would imply a difference. So is our model, can we explain the pattern we're observing? Probably not, which means the next step is to, in the model building process, is toss it out. Models they're not like works of art, just throw them out and move on to the next one. We try again, we stop and we think. We come up with another explanation. We say, look, college students have a lot of things in common. People who live near each other tend to discover things about themselves. If they discover they have a lot in common, as a result, they lead to friends. It's an interaction story. The closer you are to someone, the more likely you are to become friends. And so this would explain why we observe the clusters of friendships in all dormitories, including the freshmen. So that can account for this new observation. Does it mean the model's correct? No. Exclamation point, no. People do this all the time. They find one thing that supports their argument and then we're done. No, we constantly need to ask, well, what else does this imply? What other implications can we put to the test in an effort to falsify or disconfirm our model? We are always trying to, ultimately the mark of a good scientific practice is someone who says, look, I have done everything I can to prove that I'm wrong. I can't. I'm going to send it over to you, and now you try to prove me wrong. So a model is a simplified representation of the world. It's a series of logical statements combined to explain processes that, when combined, produce falsifiable implications, to quote my old professor. And yeah, anyway, simplified representation of the world. We create them by speculating. We stop and we think what is producing what we are observing. We evaluate models by looking at, is what the model implied consistent with the facts? Can we post-dict? Can we predict? Can we generalize this model somewhere else? Is this just college students that interactions lead to friendship, or could we test this in neighborhoods, in workplaces? Is our model capturing a more general phenomenon than what we're observing? And then ultimately, how simple is it? Is this an explanation that is rooted in just a couple of simple assumptions that can explain a lot, or do we require a lot of assumptions? So if we had to step back and say, well, what is a model of the model building process looks like this? Live and March tell us it's a 4-step process. And if there's one thing I want you to take away from this talk, other than the fact that Phil talks really fast and uses a lot of slides, is this 4-step process. It is, beat into my head from years of teaching this material, in which the first step is, look, the start of any scientific process is observation. And this is where visualization of data is so important, because it allows us to notice a pattern or result that has occurred in the world. We observe it, we go, and the most interesting observations are ones that run prior to our conventional wisdom, or something that goes against what we're expecting, which then leads us to speculate. We develop an explanation for the process that could have produced what we are observing. And I think, again, I think people are quite good at this. I think people look at something and say, I bet it's this. And then they stop. The all important step is to then think what it would have to be true if my explanation is correct. What is an implication that would follow from this logic? What else should we expect to observe? And then critically, and this is where the science comes in, we need to put it to the test. We need to see whether the implications of our model are supported in the data. Is it consistent with our hypotheses, or does it go against it? If it goes against it, what do we need to change? We need to go back to the drawing board. We observe, we speculate, we develop implications, we test. We observe, we speculate, we develop implications, we test. Now, this isn't exactly novel, but codifying it in this way, I think, is a good way to just think about, if you're trying to explain something, where are you at? Do you have a speculation you're looking to test? Do you need to gather new data in order to test that argument? Or are you still just trying to figure out what is evidence in favor of my argument? And so I give you kind of a bizarre example, or maybe not the sexiest example. I thought about going with the example from either Civil War and like, why do atrocities take place? I threw that out. I almost went with the current puzzle that I am struggling with on a day-to-day basis, which is, why is my cat pooping on the floor? I'm working on it. I still haven't cracked it. But the model building process is applicable far beyond the social sciences. And I want to just lead with one big historical example of what this process has looked like in the accumulation of knowledge over the centuries. And really, this is why I asked whether people had taken an astronomy class. And this, I actually do want to go to the chat. Can anyone tell me what this is a picture of? I need more litter boxes. I've tried that. I know, that's a good speculation, right? Nah, doesn't work. Well, we can talk about this in the Q&A. This is not the sun. Aha, we got it. Dave's got it. This is Mars. If you were to go out in the nighttime sky and plot the path of Mars every night, you were to go out and say, all right, this is where it was today, there's what it was the next day, and you were to plot its pattern, you would notice something quite bizarre. It appears to move one way, and then suddenly it just reverses, turns around, and gets headed back in the other direction, which is quite puzzling. Why is this happening? And this was a huge puzzle for like astronomers in the past. Why does Mars move backwards in the nighttime sky? And the reason this was a puzzle is because of the model of the day, the speculation about the process. And the current model at the time was, look, the Earth is at the center of the solar system. Earth is the focal point of creation. Everything, all of the objects in the heavens rotate around us. And ultimately that the heavens are in perfect harmony. And objects must orbit the Earth in circles, because circles are apparently, or at least believe at the time, the most perfect shape. But the implication of that is, well, if that's the case, then Mars shouldn't be moving backwards. Mars should be predictably moving in one path. A circle shouldn't ever go backwards like that. So, but it does. If you look at the evidence, it doesn't fit the model. So what do we do? How do we figure this out? Well, we got to come up with a new model, which is what Ptolemy did, around the turn of the millennia. He, around 100 AD, ends up saying, I even got the picture, right? He's like, aha, I've got it. Here's my model. He says, look, the Earth is at the center of the solar system. Planets are orbiting in circles, but they're just also orbiting in mini circles while they're orbiting on the circles. And so what we're observing is every planet is orbiting us, but it's going in this epicycle. And so what we're really seeing is it completing its mini circle around the larger circle. So we're still good. We're at the center. The planets are still moving in circles. It's just circles on circles. So it's a model. And it is able to explain why Mars moves backwards. Now, if this is correct, what else should we observe? Well, we should be able to use Ptolemy's model to predict where all of the other planets are going. And it does. If you actually use Ptolemy's model, it does a pretty darn good job explaining and predicting where the planets are going to move. And that's why it became the consensus model for centuries, because it was able to predict, it was able to explain. But it doesn't do so perfectly. And these mistakes, the inaccuracy of the model, started to become more apparent over time. More observation led to more data collection, which led to more inaccuracies. Also, I should mention the Islamic astronomers tended to be more forward thinking on this and tried to reject geocentrism, but that's a whole other discussion. But new models for the solar system are ultimately proposed in an effort to explain why Mars moves backwards and to explain why suddenly, like, we can't explain precisely where Venus is. So Copernicus comes along and says, all right, guys, I got a new model. We're going to change the assumption and we'll be able to explain where the planets are. Now we're going to say, look, the sun is at the center of the solar system. Earth is an object which orbits the sun. Everything else is orbiting the sun. The moon, however, does orbit us, but everything moves in circles. So we have just a fundamental shift in our explanation for where things are. The sun is at the center of the solar system rather than us. And this is often viewed as like it was rejected on religious grounds. He was trying to upturn the Bible because the Bible implies that the Earth is at the center. Not really. Copernicus was a devout Christian, and he thought an inquiry into the manner of the heavens would reveal things about our Creator. So it's not so much rejected on the grounds of this goes against religion. It's often not quite accepted because it doesn't do that much better of a job than Ptolemy. As a model, Ptolemy's actually still works pretty well. This doesn't really improve a whole heck of a lot. And as a result of this, we get other models emerging. So Tycho, who is just a fascinating individual, he goes off and he's insanely rich. He goes off and basically builds a laboratory on an island and lives there for like years and just spends every night looking up and plotting all of the movement of the planets. But at this point, again, only with the eye. We don't have any other technology. So he says, all right, guys, it's something else. In this case, the planets are orbiting the sun, but the sun is orbiting the Earth, and the Earth is still at the center, and the sun is orbiting like all of them around it, right? Completely different process that can explain why we're observing what we're observing. So what we have were 3 different models of the solar system, all which will rely on different assumptions, different speculations, in an effort to explain why we are observing what we are observing. So how do we determine which model is the most correct? At this point, we have speculated, we have built models. We now need to basically see which one wins out, which one is the most right. Which one can't we falsify? So in order to do that, we think about the implications. What would have to be true if these were correct? We then gather data, and this was done for centuries. And ultimately, it's new methods of data collection that challenge Ptolemy's model. Galileo's invention of the telescope enables us to start seeing sunspots, implying that maybe there are problems out in the solar system. It's not fixed and eternal and perfect. We also spot the moons of Jupiter, which is clear evidence that an object is orbiting something other than us. You get the supernova of 1604 observed by a man named Kepler. This is an actual picture from 1604. No, this is a recreation. But it implies that, oh yeah, there's something different. Like things aren't fixed in a mortal. There are changes that happen out in the heavens. So, but you also get new developments in other disciplines that then enable us to explain. So Newton goes off and writes his crazy book. He spends like 10 years writing it. It gives us calculus. It gives us all these new calculus, which is what is going to enable us to do the predictive modeling I'm going to do later. But he also gives us new mathematics and new physics to explain why things move the way they do, which then Kepler takes. He develops his new laws of planetary motion. We don't need to go into them, but he implies, nope, guys, Earth is rotating the sun, is orbiting the sun. The sun is at the center. It's the orbits are ellipses. That's the key. They're not circles, and they shift in speed depending on where they're at. And this is ultimately what leads us to our model of the solar system. And this is correct in the sense that we have not been able to falsify it other than we did toss out Pluto. RIP, it's no longer classified as a planet. But this is our current conception of the solar system. Planets move in ellipses and at slightly different planes. And so the reason Mars moves backwards is just a function of, well, it's moving at a different pace, and it's all about where we are relative to it. And there you go. There's your explanation. We observed, we speculated, we developed implications, we collected data, we put them to the test. And this enabled us to learn and construct a model of the heavens. This took a long time. Now, data comes in 2 places. It's both the observation and it's for the testing. The science, the all-important steps, are these 2, 3, and 4. We learn from data. We use data to guide our initial thinking, but data is a means of putting it to the test. The data isn't steering this conversation. Other than that, it allows us to speculate. Data, in other words, does not by itself enable learning. Data is a means of testing the implications of our models. It is a way of confirming or supporting our suppositions, our beliefs about the world. So, I mean, we can look at tons of examples of this, and I will keep an eye on time here. But I mean, so I think some people just kind of get this backwards. John Snow in the London cholera outbreak of 1854 is extremely well known and talked about as not only one of the first causal inferences, but one of the most influential data visualizations, in which he was able to plot the fatalities from a cholera outbreak in London and pinpoint, saying, look, most of the deaths are occurring right around here. what ends up happening is it must have been something in this area. Aha, it's the Broad Street water pump, in which you can go and see a plaque today being, he identified that cholera was spreading from the water pump. And the way people think about this is they say, oh, he must have just plotted the data and then gone and realized that there was something happening. It's completely the other way around. Good book about this is called The Ghost Map, in which really what he was doing, and he had been working on this for years, the dominant theory of disease at the time was miasma. Disease was spread through bad air. John Snow, it's actually, right, like not the John Snow, he spent years accumulating evidence which contradicted this. He constantly tested and looked at outbreaks, looked at the data, and found that miasma, bad air, could not explain the patterns he was observing. And so when the Broad Street outbreak occurred, he was ready. He was able to then go gather this data in an effort to support his model, his speculative model of how cholera spread, which was related to the water. And he, in order to, again, gain evidence, it's not enough to just plot the visualization. He had to argue this for years. He had to interview everyone, interview the relatives. He had to gather as much data as possible to seek out every implication that could ultimately support his theory. I mean, we can look at examples of this everywhere, but it's our speculation guides our data collection. We observe something, we then collect data, and then we use it as evidence to confirm or support our, technically we don't confirm, we can only disprove if you're a Popperian. Florence Nightingale was actually one of the first users of the pie chart. She was number 2 and that we have in record of using it, in which she's, we think of her as a nurse, but she's observing all of these deaths from the Crimean War, and she ultimately collects data because she has a hunch that this is actually, most of the deaths aren't coming from battle, they're coming from disease. So if you plot the deaths that were occurring at the time, like by the month, the color here, blue, is deaths from disease. These are deaths from battle. These are deaths from other causes. And the reason she collected this and displayed it was, look, guys, if you guys think that it's all about battle and not about disease, then why are we observing this? The data was a means to support her argument. I was going to go into Osamoglu, Johnson, and Robinson. I won't get into the details of it, but they have a reason. There's a reason why we observe that population or GDP per capita today is related to the settler mortality rates of your country in 1500. There's a reason for this. You can ask me about it later. The point is, data does not by itself enable learning. Data is a means of testing the implications of our model. It is by figuring out ultimately whether our models are right or wrong that we enable learning. So how can so many people, people are often quite stubborn. Again, they don't like to look at the implications that can prove them wrong. And in the case of the ghost map, again, John Snow took years to argue against miasma. Why were people refusing to look at the evidence and update? I mean, this is really like one of the key points from this is, in order to learn from data, we need to both speculate, but we have to be willing to be wrong. Discovering that our models are wrong is good. Refusing to acknowledge this and refusing to update our models is bad. And you can look at historical examples of this just to see what people were stubborn about. So there's a really famous economist who maintained that, he studied this for years, that sunspots, the number of sunspots a year, could explain economic cycles here on Earth. So he's plotting the price of corn versus the number of sunspots. And he has you can go get a book and it's you fold it out because he's doing this all manually. He was convinced, despite the fact, I mean, I will spoil it for you that no, sunspots don't explain economic activity. But this is something that he had an explanation, and he refused to eventually look at the evidence that proved him wrong. He selected only the evidence that confirmed his theory. Similarly, astrology, it's a pseudoscience now, but when it started, it was actually a pretty legitimate scholarly inquiry. Do what we observe in the heavens explain things down here on Earth? And they actually collected a lot of really good data to try to test this. And a lot of our data from learning the solar system comes from these guys. But it's the refusal to admit eventually, hey, there's no evidence, it doesn't support our theory, that leads it to become a pseudoscience rather than a practical science. Fisher, who is the father of experimental methods, the developer of maximum likelihood estimation, who again is going to enable me to show you guys a predictive model in a minute. He was someone who he's the first person to actually be able to enable causal inference, X caused Y. He stubbornly maintained for the rest of his life that smoking did not cause cancer. He was also an avid smoker. He refused to look at the data that went against his speculation. So no matter how smart you are, people can be quite stubborn on this and refuse to give into the evidence. The process of science means we have to be able to admit that we are wrong. And if our goal is to learn from data, we need to speculate, build models, develop their implications, think about, well, what had have to be true, and then we have to put them to the test. Doing so is how we learn about the world around us. So I mean, this might be feel a little bit far afield from that original question of okay, we just want to move past visualization reporting to building models. Why are we talking about sunspots and the solar system? the answer is like building models is the way that we get past this. We use the data, we use visualizations, we use reports to generate speculations that we then can put to the test. So we're going to shift gears pretty dramatically here. We're going to look at an example in some depth. Again, hold on to your butts, because we are now going to jump into building models of the Texas Stars, a minor league hockey team down in Texas. We're going to look at some AHL advanced analytics. Now, technically, I said Texas Stars just because it allowed the, hey, 1-2, and we're mostly going to focus our attention on the Milwaukee Admirals, which is why I asked. They're actually, as a team, suffering a pretty hard time right now. Their season was not on because of the pandemic. So, hey, let's all support Milwaukee Admirals when they get back to playing next season. So just give you again some context. What I want to show is the journey from reporting to advanced analytics. That's the goal here. But I want to talk through that process. And what's cool is normally we do all these things and I can't show them to you because it's all under NDA. This one we can show to you because it was purely pro bono. So as a side project during the pandemic, a few members of our team started working with collecting and gathering AHL minor league hockey data. And then we discovered that at AE, we had a contact who actually worked within the Milwaukee Admirals. And we were like, hey, can we show this to you guys? Do they have any analytics? Can we end up, we send them over some stuff. And we eventually ended up meeting with their entire coaching staff and front office to talk about this work, which for me was like a dream come true, because secretly my desire to explore and explain hockey is what led me to study predictive modeling. And I just had to use the excuse that I was studying international conflict. So this was an opportunity for me to look at hockey data and start to help these coaches learn about the game. Now I'll get to what we showed them. And this is actually where, if you're wondering, like, this is a Tableau talk, why hasn't Tableau showed up? That's where we're getting. But I want to talk about that process of how do we get from data to reporting, but then also into something else. And almost like a painfully concrete example. We'll get there. So now a lot of you actually said you went to a Milwaukee Admirals game. This is a game that they played in, and that's actually, I'm really happy. So hopefully I don't need to explain the basics of hockey other than to say, if you observe enough hockey games, you start to ask questions like, why are some hockey teams and players better than others, right? Some teams clearly win, some players clearly end up scoring more goals. Why is that? Well, you win hockey games by scoring more goals than your opponent. This is a model, just for the record. I put it to the test, it checks out. Better players are able to generate more shots and goals than others. So really, if we're trying to explain why some players are better than others, we need to ask, well, why are they scoring more goals? Like, what is the process that leads a hockey player to generate more goals than others? Why are some hockey goalies able to stop more goals than others? And for this, well, in order to answer this question, we will both observe the data, then we'll speculate, and then we'll put our speculation to the test. So this is, and I got to give a shout out to Justin on the chat. We can get data for every player, for every AHL team, and every game from 2018 to 2020. When you plot it, this is what you have. It's the location of every single shot. So for instance, one circle is a shot that took place on the ice. You can kind of see the makings of a hockey rink, right? These are the nets. These are the blue lines. This is every piece of data that we have. And what's cool about this is we have the location. We have the coordinates. We know what the time of the game was. We know the player. We know the goalie. We can learn a lot from this. We end up actually, like flipping, because really what we care about is like, all right, given a shot, we want to ultimately be able to say, why do some shots become goals and not others? And why do some players tend to take shots that turn into goals and not others? So for instance, we know most importantly, what we care about is we know whether a goal was scored. So just observing the data, we should be probably seeing a pattern here, right? And again, this is the shocking innovation. Now, this is again, like, we score goals by getting close to the net, right? Like, there's your advice, Milwaukee Admirals coach. No, it's like, in general, most goals come in from, like, the more you're able to close the distance, getting tight to the net, this is going to explain goals. But there's also some interesting patterns here. Like, oh, there's some clear angles. There's some interesting, like, cluster here. What's going on? Why is this happening? And ultimately what I would say is, does this data, like, if we just use this, if we had nothing else, does this data tell us which players are better than others? Because I think this would be the point where the business intelligence stops. We have this data set, we put it into some dashboards, and we can start exploring it. And the answer is, like, kind of. I mean, we can look at who scores the most goals, which goalies have the most saves, that sort of thing. So, all right, we can build some dashboards. We can say, like, here's every shot for the Milwaukee Admirals in 2018. You can see where they scored goals versus where they didn't. Interesting. They scored them in close to the net. There you go, guys. We nailed it. But like, what can we learn from this? I mean, we can say, like, a player, yeah, this is where you tend to take your shots and this is where you don't. We can give you, like, your shooting percentage, and we can, like, say how many goals you're averaging per game. We can look at a goalie and say like, well, how has your performance changed over time? Are you facing more shots? Where are you giving up goals? But it's hard to actually answer questions. This looking at the data like this just leads to more why. Why are we seeing this? The data observing it leads us to want to speculate and understand the process. So we've gotten here, which is the reporting. We have purely descriptive. We haven't really learned things that are evident in the game of hockey that we can ultimately want to try to understand. We've gotten to the business intelligence. Now we want to take that next step. The data by itself doesn't tell us things we want to know. And this is where we do need to theorize and put on our Clausewitzian hats about why some teams manage to win. And this is both a theoretical assumption, but frankly, it's pretty darn supported. Hockey is a game of luck and skill. And this can be frustrating for people who want everything in life to be deterministic. Sometimes you don't win, despite the fact that you played really well, because the puck is a jerk and didn't bounce the right way. Sometimes teams, sometimes players just get lucky. This is true in life, in most of our pursuits, but it's especially true in hockey because it's played on ice. People are hitting each other. The teeth are flying everywhere. There's a lot of luck. And individual hockey games actually tend to be kind of a coin flip. It's only over the course of a season that we can actually figure out whether your team is good or not. So if we know this, when we look at the data, we are getting both things. We are seeing luck and we're seeing skill. And we don't have any way to parse those out. We don't have a way to say who is good versus who is just getting lucky. We want to try to measure skill, meaning we want some analytic that can tell us how well are you playing beyond just looking at the outcome. How are you doing with the process? And this is where the advanced analytics come in. We can start building models. Well, what does that mean? What does that actually, like, I can say that and it sounds kind of cool. Yeah, I'm applying machine learning to hockey data, but like, what am I actually trying to solve? The answer is this. For every shot taken, I want to know how likely was that to become a goal? Based on the historical data, if you took a shot from this particular point in time at this point in the game, you're this player of X skill, how many times out of like 1,000 is that actually expected to go in? Where good players are ones who maximize their goals and expectation. Sometimes it doesn't go in, but over enough events, players that are taking on average, the best shots will be ones that are ultimately the best players. So for instance, and this is where the gifts are coming in, let's look at an outcome here. This is from the San Diego goals in December. Giovanni Fiore, 133 into the first period. He did not score on this play, but let's look what happened. All right, he comes in. He's got a wide open net, wraparound. Defense manages to just barely stick his stick blade in there and deny him a goal. Great defensive play, but it was still a really good offensive play. He jumped in, he created a chance, and he became extremely close to scoring. The question is, how many, out of 1,000, how many times would we expect that to go in? We should give him some sort of credit for this goal, but how do we do it? Because the problem is, you'll get stuff like this. This is Texas Stars versus Chicago Wolves. If you're wondering how I got these, I was able to take the predicted probability of every single goal and then look at the top and the bottom, and then I had to go dig through video highlights for a while. But so this one, it actually ended up going in. And let's look what happened. Joel Hanley is getting ready to take the puck. He dumps it in. And what's this? It somehow ends up in the net. So let's watch very closely. It goes down. It bounces out. It takes a left turn and somehow manages to scoot into the net like the magic bullet with JFK. It wasn't actually a magic bullet, but in general, right? This is an incredibly lucky bounce. Joel Hanley should not be getting that much credit for the play. All he was doing was putting the puck in. So if we want to figure out this idea of, well, on average, how many times did you score from that shot? We need a model. We need a predictive model that can say, what is the probability that a shot will become a goal? Meaning we have some features. We have, we know the shot location, we know the player, we know the game, and then we know the outcome. We want to learn from the data, what is the relationship? What is the historical pattern? And if you're wondering here, why are we talking about hockey, especially after talking about astronomy? This is the same thing we do in every walk of life when we're building models. It's the exact same process. If you talk about models of whether or not you're going to be approved for a mortgage, exact same thing. Features, outcome, learn the relationship from historical data. The data is a means of learning, but the model is extracting the historical pattern. And what's really important here is in order to get a model to learn that relationship, we need to speculate about features in the data. We need to speculate about things that we think could matter. And for this, we need some subject matter expertise. We need to know something about the thing we are studying. Because this is the part that if I could just go on a mini rant for a while, it would be people say things like, oh, data scientists spend all their time preparing data and cleaning it and wrangling it. And they should be spending all their time on modeling. And it's no, the modeling is the easy part. The speculating about the process and then converting that into, all right, I'm going to give this model this variable and it's going to try to proxy for this thing I think it cares about. That's the hard part. That's the work. And the data, like most importantly, the data is not going to do this for us. The data comes to us with, these characteristics and ID, and we have to try to figure out what is present in that data in order to enable a model to learn. A model can help, but we need to think about the data and engineer, come up with some new variables that we think are going to matter. The data will not do this for us. We must speculate, we must create variables, and that'll enable us to put it to the test in a model. So, right, if you go back and look at that, like we can look at a portion of the data and go, all right, well, so what's going on here? How can we explain and model the probability of a shot becoming a goal? And there's, again, it kind of jumps out right away. Let's just calculate the distance to the net, right? Shots close in tend to score, shots that are farther away don't. But there's another thing here, right? We can calculate distance. We can also struggle to remember our high school geometry, which is, this was an embarrassing, like us sitting there trying to, cosine and all that. And you can say, well, what's the angle to the net? Because again, there are these interesting kind of angles that emerge. Now, nothing in the data told me that I needed to add this feature. I just said, look at the data. My knowledge of hockey, I used to play. I understand some angles are better than others. So I'm going to create a feature for that for a model. Subject matter expertise, speculation matter. So just using those two, can we predict? Well, let's just go build a simple model. We don't need to do anything more complex. Let's just go toss that in, train a model to learn the pattern and see what we get. So here's two simple models and what they learned from the data. The one on the left looked at the distance. The one on the right just looked at the frank coordinates and said, based on everyone around me, how likely is it to become a goal? And you can see, right, it's a linear relationship. It basically says, all right, these are likely to become goals, all the others aren't. As opposed to this one, which is it's a bit wiggly, right? It finds some areas it likes, some areas it doesn't. But in general, they tend to agree. The closer into the net, the more likely you are to see a goal. Right? So if we go back to this particular shot, both of them basically agree that, yeah, about 1 in 4 times, you should expect that shot to be pretty good. That's a good shot. Good job, player. We're going to give you credit. Similarly, this goes in what, 4 times in 1,000? This is an incredibly fluky play. This is actually the least probable goal scored in my data set. And I just managed to find a video of it. So are these models good? Well, they're better than not having one. And this is the point that kills me with a lot of, like, when I consult and I build things, they're like, well, how do I know if this is any good or not? And it's like, okay, well, everything should be relative to our baseline. Is Copernicus's model good? Well, is it better than Ptolemy's? Is it better than what we currently have? So we want to have something that we can then use to start exploring and adding in new data. So in general, the answer is they're okay. There's they do pretty well at identifying shots that don't become goals, but they struggle to identify those that do. And the reason for this is, I mean, we can do all these goodness of fit, and I will say visualization is quite important for this process. They do a decent job, but they're missing a lot of things. We want to throw other stuff in here and then see how it matters. So we can say, all right, look, we're looking at it just from like 2 dimensions. Let's look at it from 3 dimensions and think about the time between shots. Let's think about like, oh, okay, if you get a rebound, it's more likely to go in than if you didn't. We can look at the flow of the game, look at special teams, say, oh, look, goals tend to come from, they're conditional on how long it was since the previous shot. We can do all of this exploration of the game of hockey to then feed into a model to see, hey, what matters, right? We can come up with these features, fit more flexible models, slowly increase the complexity of our model, and see how well it does in explaining the results we observe. So you end up getting different models that make different assumptions that treat the data differently. We then go make predictions using all of them. And so, for instance, the best performing model actually gave this a 0.64. It would dub this as one of the highest probability shots that didn't go in. This was a really good chance according to that model. We can then start to say, well, like what matters? Like how do specific variables predict things? So like this is where we can start to understand what are the causes. I mean, it's, correlation, not causation, but people always say that and then they forget that like, well, correlation is necessary for causation. We should then at the very least investigate it. We can say what variables tend to matter the most. Turns out, yep, it's distance, but also that time differential is quite important. Ultimately, this is what the process looks like. This is the nuts and bolts, and we're getting close to the end, and I will stop talking, and mercifully, I will stop talking. Ultimately, we can use all of these models in order to compute expected goals, meaning we have an advanced analytic. Every shot now has a new column, a new feature that says this is how likely it was to become a goal. We actually have like 20 some columns because we have a bunch of different models that all make different assumptions and then look at different information. In other words, we learn something from the data so that we can pose it to the Milwaukee Admirals coaching staff and help them start answering some questions about the game. So for instance, and this is really, I think, I mentioned people, hey, I'm going to be showing some of my AHL stuff. This is, I think, what they wanted to see. This is where the real fun begins. And it's also where Tableau enters the picture, because it's one thing to have a model. It's another to be able to actually like quickly and rapidly explore the model and make various calculations and apply it, and then to really start to see and understand what it's predicting and why it's predicting it. So like we can look at every game, break it down to a bunch of things and ask, did we actually play better than our opponent, or did we just get lucky? Right? So for every game, we can look at a report. We can say, all right, here are all of the shots that took place. Here is they're scaled by the quality of the chance, the expected goals of the opportunity. We can look at a game and say, all right, in terms of expected goals and the quality of shots, were you outplaying your opponent? It's like, all right, through the first period, they were pretty even. Then the Milwaukee Admirals took off in the second period. By the end of the game, had 3 goals in expectation, where Chicago had 2. They scored more in reality. I think they actually got a couple empty netters when I went and looked at this game, which is why my expected goals doesn't look at empty net shots. But in general, the answer is like, yeah, they played pretty well. The process by which they played the game produced the result that you want. But you could just as easily lose a game where you outplayed your opponent, because hockey has a lot of luck. What you care about, if you're monitoring something over time, is the process right? That's what we care about, not the outcome. So like this game, they played pretty dead even. They actually outplayed their opponent like the entire game. They ended up losing 2-1, despite the fact that they were pretty even on expected goals. We can also then start to give players like which players played the best, who contributed the most. And in this particular game, it's like, well, guys, you played really well. Then it looks like you gave a power play and then you gave up a goal late. Like, I mean, you kind of got a little unlucky, but also like, hey, don't give them 5 minutes of power plays back to back to back. You can also then just look at something like this and be like, what, 9-4? The game was 4-2. They scored 7 goals in the second period. What the hell happened? Like, let's go look at our strategy and figure out what did we do in that second period that caused this massive explosion of offense. We can ask other questions like, how does our team's offense compare to the rest of the league? So like the Texas Stars, which is why I built this originally, we can say, all right, let's look at their expected goals by each area of the ice compared to everyone else. The LODs for this in Tableau are nuts. It took me forever. But what you can start to say is like, how do you compare to all of the other teams? And you can start to see like, oh, wow, okay, so they generate more offense than the rest of the league through the high slot. The Texas Stars shoot less from the points, but they tend to generate most of their offense. They prioritize shots here. This is the same type of analysis that the NBA is doing right now to figure out where teams selecting their shots. And in the next year, their offense got a little bit worse. They still like to drive that strategy through the high slot. We can look at the Milwaukee Admirals. This was really cool because I got to show it to the Milwaukee head coach and be like, this was the team before you joined, below average offense across the entire board. This was the team the next year when you joined, above average basically across the board. Something has happened that is explaining this, that you guys are now pretty darn good on offense. Most of your offense tends to drive from the left center of the ice. Now, I have not watched a Milwaukee Admirals game in 2 to 3 years, but I now have the data that can start to like at least explain some of what is going on. The real value of this is putting it in the hands of someone who knows very well what's going on and then can start to ask questions like, why don't we shoot from the right circle? Is that because we have a bunch of people who are left-handed and shoot from this side? Interesting. We can then look at players, like who's generating the most chances. Like this player, Jason Robinson, this is his 2020 season, just graduated the NHL, should be rookie of the year this year, but he's going to lose it. That's for the Dallas Stars. We can say which of our players are generating more than average. We can look at a goalie and say, how good are they? So the Milwaukee Admirals, again, I got to talk to his goalie coach, and this is really cool. He is by far the best goalie in the league. The reason that they're doing really well that year before COVID stopped it, they probably would have won the cup, is the fact that Connor Ingram is a freaking beast of a goalie. He stops so many more goals than you would expect for an average goalie. He is a massive outlier. Something in his game translates to him being really good. We now have this new analytic that says, hey, this guy's really good. These players, no disrespect to Charlie Lindgren, but he apparently isn't that good. All right, to start wrapping this up, what this really led to is we can see that, for instance, our favorite team, the Dallas Stars, have an opponent who's about to be playing a third-string goaltender, and we realize that we have AHL data on him, and we can scout for his weaknesses. So I went and looked at Michael Hutchinson because the Stars were about to play him, and I was like, what's going on with this guy? What does he look like? And I can say, all right, he's pretty good. He's pretty good in the slot, but he's really weak on this particular circle. Shots from the left-hand part of the ice tend to beat him more than you would expect. And so at this point, I was fruitlessly trying to contact the Dallas Stars coaching staff to give them this scouting report. Like, hey, guys, shoot from the left, right? Advanced analytic can drive scouting, can drive decisions. But honestly, I wasn't able to do this, and they seem to have figured it out anyway. If you watch the goals that were scored in the next couple of games, this was like the first goal we scored, and I was like, aha, from that slot. And it's actually, it starts to uncover why it's happening. He's a lefty. He catches with his right hand. Most goalies catch with their left. And so he ends up being beat to his glove on this side quite a bit. And that's probably what's going on. If you're a coach, you can say, all right, let's run some glove drills. Let's try to let's close down that angle. We beat him again, right? Watch, the game 7 had just gone down. Kiviranta scores in the left circle. In overtime, frankly, I can try to find a way to inject this clip into every single presentation I ever give, because Kiviranta scores in overtime, game 7, hat trick winner, first ever game in the playoffs, comes out and becomes just a living legend and sends us to the conference finals. And I could sit here for an hour and watch this on replay, but I will spare you. We build models in order to learn about the world around us, even if it can also tell us the weaknesses of our opponent's goaltenders. Advanced analytics can do us a lot, only because we built models that based on our speculation, based on our knowledge of the data. Subject matter expertise is incredibly valuable, but we need to be willing to put it to the test. Once we have a model in place, we aren't done. And honestly, once you build a model, that's where you start to generate all of your ideas. Like, well, what if we gathered this data and then we put it into the model? We can look at what the model is producing, see where it's doing well, see where its mistakes. Again, getting things wrong is incredibly useful because it enables us to learn, to speculate about why, come up with a new variable, put it into the model, and see if we can do better. We are constantly trying to improve. Science, it turns out, is just as useful for studying the stars as it is for studying the Texas star. So I want to wrap up at this point. I will, again, mercifully try to spare you so we can have some Q&A and move on to other topics. So now what, right? That was the topic. That was the question, the motivation. We want to get into advanced analytics. All right, you just showed us a bunch of like a ton of slides. It's almost 2:50. What do we do? What do we take from this, right? What we model building, science, analytics, what do we do? I want to just leave you with one thought. I've actually, I think, kind of matured in this, or my thinking on this has evolved. Previously, I would say, go read these textbooks. I would say, look, guys, like you just need to go read Kuhn and Johnson, and then it has recipes for all of the models you want to build. And people look at like I'm insane, and probably justly so, because most people don't pick up textbooks in their free time to read. Now, the answer to what I think you should do isn't in a textbook. The answer isn't from computer science, statistics, math, or even the social sciences. The answer comes naturally from television, which is why I asked you guys about The Good Place, which is, for my money, the best television, best comedy, most profound show that has been on in decades. So Mike Schur, if you're familiar with The Good Place, I won't spoil it for you, but it's essentially an exploration of the afterlife. And Mike Schur, the writer who also wrote The Office and Brooklyn Nine-Nine and Parks and Rec, so basically he's like a gift to humanity. He's a writer, and he had this to say about the show. The basic question, the basic exploration of the show is, what does it mean to be a good person? And this is a broad, big question that can lead us to run down so many different lenses, so many different theories. We can run the full gamut, explore everything out there about how to be a good person, and it just starts to get exhausting and it starts to get overwhelming. It is asking too much of people to dedicate their lives to becoming monks, to reading philosophy every single hour of every single day, to shed all their earthly possessions and try to be a good person. But you know what's really important is if you're just trying to be a good person, if that's at the front of your brain all the time, if you are just asking yourself constantly, am I doing this right? Am I doing things that are good or bad? Could I be improving? What am I doing right now that maybe could be better in the next run? If you're just asking the questions, that's kind of the key. And really, the main focus is just try to be a little bit better than today than you were yesterday. Now, I'll say it's more important to be a good person than a good data scientist. I hope we all can agree with that. But I do think we can easily amend this for that journey into data science. It's not about textbooks. It's not about going and learning how to code. Quite simply, and this is going to be from me, the stealer of quotes, because I'm not a writer and I'm not sure what other title to give myself, we'll amend this just a little bit. The basic question of whatever the heck this talk was what does it mean to be a good scientist? We can run the full gamut on this and explore every possible theory about how to be a good data scientist. And it starts to get exhausting. Believe me, I've been there. I try. It is asking too much of people to become grad students and shed all of their earthly possessions. Again, I've been there. I don't recommend it. You know what's important? If you're just trying to learn about the world around you, if that's at the front of your brain all the time, you're saying, what is it? What could explain what I'm observing? Could I come up with a better explanation? Am I right? Am I wrong? Am I generally doing things that are good or bad? Could I be improving somehow? If you're just asking the questions and speculating and putting them to the test, that's kind of the key. Just try to be a little bit better today than you were yesterday. this is the secret to building models. This is what that next step looks like. This is the secret to good science and how we learn about the world around us, regardless of the subject matter, whether it's astronomy, whether it's hockey, whether it's disease. This is the answer to the now what of analytics. So thanks for listening. And for advising regarding data science, board games, and/or AHL scouting reports, do feel free to email me. I am not sure where we're at on time, but we might have some time for Q&A.
Thank you so much, Phil. I am so glad that I asked that question and that you got what I meant. That's awesome. So did you incorporate then whether the goal? Oh.
What's that?
I'm sorry, did you incorporate then whether the goalie was left or right-handed into the next version of the analytics?
Don't have it in the data, which means
Okay.
we need to actually, I asked Justin to go get it for me, and I think he did,
Okay.
but I hadn't yet put it in. But like,
Cool.
you see how like that thought then
Yeah.
sparks what data should we be including, right?
Yeah.
Like that's why
Yep.
it's so useful to have the model, right? Yeah.
Yeah, that's awesome. Thank you so much. Amazing. I'm gonna watch it over and over again, probably, and share this with so many of the business users. You know, it comes from them. Why would this happen? What are the possibilities? Why would you think this could happen? And let's test them all. I know there are some questions.
Yeah, also it looks like someone might hold the secret to my my current puzzle, which is involving the cat.
Yeah.
I mean, I will say we did take her to the
consulted.
vet and we actually dropped off some poop, which was not a pleasant experience, and they never got back to us. So I'm going to inquire about that again. I wonder if this is the case. I will say, if Krista, if you've got it, like, a prize will be coming your way. If your speculation bears out, right, you know, your model will win.
And sorry, I hate to say it's been there, done that. So yeah, and it's like $76 auto ship for the cat food, you know, that comes. So yeah, I am prescription urinary. She's not been a naughty cat since.
Thank you. So here's one from Mary. How do you look at a variety of models with different outcomes and determine which data features are providing a more accurate model? How do you avoid getting stuck in the weeds with a model that could be misleading? What's your process?
Great question. This is actually like a very broad, like deep question. Like,
Yep.
you could spend hours talking about this. I will say my first advice is, one, any solution that you're providing is entirely contingent on the problem. So for instance, in the case of my hockey data, I know the problem. I'm trying to estimate something directly. I could, for instance, get an incredibly predictive model by including like, did they score or not? Because you know that at the time, like, what was the score of the game at the time? Like, we could come up with a perfectly predictive model. So like, but there is, like, things like certain additions to the model might improve accuracy, but that's not what I'm trying to optimize on. What I care about is this able to explain, given what we knew at the time, whether a shot was going to score? Now, that doesn't quite answer your question, but knowing the problem guides a lot of what you include in models and whether it is relevant or not. The other approach that I recommend, and this is the Scott Page, the model thinker, is you shouldn't try to get to one definitive model. I mean, frankly, what's happened with machine learning right now is the reason, for instance, boosted trees are doing so well is because they are ensembles. They make use of thousands of models under the hood. So if we train a bunch of different models, and I actually thought about showing this visualization, was like, for a given shot, you'll have like 7 different models all looking at different things that then give us, you know, various estimates of where it's going to be. And so looking at working with many models, you want to start to figure out, is there consensus? Like, so if you look at like a hurricane forecast in the spaghetti plot, we don't just look at one, we look at where's the general trend. We look at, I assume people know the spaghetti plots, right? When you look at hurricane, I had to learn a lot about hurricane forecasting because I live in Florida. So you want to look at where most of the models, where's the, on average, is it looking to go? Now, the other thing is like knowing what to include. Again, it comes back to that problem. I remember using an example of this when I taught, which was, if you try to build a predictive model of, like, let's say a student's grades, and you end up trying to say, all right, given what we know about a student, their life, you know, their family, you know, do we see that they are going to be, you know, score well in the test or score low in the test? And you get things like, well, if they're enrolled in an after-school care program, they score worse, which the data then would say, okay, well, if we just toss out after-school care programs, these students will do better. Which we know, well, that's insane. It's the reason they're in after-school care program is because there's something going on in their life. You know, maybe their parent, it's a single parent home, and then they're struggling, and there's a large family. Like, that's an example of, well, do I include that feature in the model? Well, if I'm trying to predict, yes, because then I can enroll in it, I can employ an intervention. If I'm trying to explain, yes, I can include it. But if I'm trying to then say, like, well, what should we do? we need to know something about the process. Like we need to speculate about why we're observing that result, and definitely we shouldn't cut out after school care programs. So that's a very all over the place answer, but it's a hard question and it's a really good one.
Yeah, thanks. I think the what should we do? I'm pretty sure that's what all the business users of my dashboards want to know. And one more question here. How did the Milwaukee Admirals coaching staff react to your analysis and the models?
I mean, they thought it was really cool. They actually were quite, they're like hockey players, right? So they're not like data people, but their questions were really good. For instance, like, so why are we seeing that a goalie has this weakness? Their immediate question is not like, oh, well, this is what's happening. Their immediate question is, well, why? Is it because he's giving up tips? Like players right in front of the net tend to deflect it and he's weak on those. Is he weak through screens? They were very interested in this stuff purely from based on what we already know, how does this conform to our expectations? And then really it's more of a guide for them to go further into film, further into the study. And even they asked him, like the general manager is really thoughtful. I think his name's Scott Nichols. So if they ever end up watching this, he gave a really fascinating answer to like, so should we be showing our prospects like how they're like their expected goals, their hey, look, you tend to take shots from this area or not. And he was a bit worried actually about showing them models because then they might become so obsessed with their metrics that they just kind of forget how to play the game. They get rigid, they get locked into this, they end up being a cheaty where they don't know what the optimal decision is, so they don't make it. So they asked some really interesting questions about what data we have, but in general, so we're still trying to re-engage with them because again, they're suffering through a hard time right now. The organization was shut down for the year, they've had to let people go. So we hope to re-engage with them when they pick back up. I hope that we'll be able to actually give them all this stuff, but it's also a matter of how do you give someone analytics? For us, our answer was, we don't want to tell you what to do. We want to provide you with the data so you can explore.
Yeah, and one more I'm going to sneak in, and then we'll move on. Did the Admirals help you out beforehand?
Nope, this was purely a fun exercise that we were like, wait, we know someone here? Oh man, we could show this to them. That's
awesome. Okay. All right. Well, thank you so much. Really appreciate you talking to us, and we will have this recording for you. I'm going to get back to the presentation. Okay. I'm going to let Brandy, if you would like to go ahead and talk about our alternating tugs coming up.
Yeah, happy to. I'm sure that you guys are aware, we kind of have 3 Tableau user group meetings that occur in the state of Wisconsin. So we have the Wisconsin group, which started at the end of 2019 and has always been virtual so that we can get people from Green Bay, from Eau Claire, from Racine, from different areas of the state and serve them and act as their Tableau community. So those meetings happen January, April, July, and October. And at the next meeting, we actually have somebody from the Green Bay Packers coming to present on their voice of the customer, and then as well as a Tableau Zen Master who just came out with a new book. So I would not miss that meeting. It's going to be a good one. And I'll post the link in the chat actually. So you can go and register for that right away. But that meeting is coming up, like I said, in July. We also, obviously the Milwaukee group, that's what this group is for. So we also have quarterly meetings, and our next meeting in August is actually going to be a partnership with the Phoenix user group where we're going to do some hands-on workshop stuff. And like Josh mentioned in the polling at the beginning of the meeting, it's like opt-in, you don't have to do the hands-on stuff if you just kind of want to watch and learn. I mean, I know I learn a lot from just watching how somebody else uses Tableau, how somebody else does something. I pick up tips and tricks along the way. So definitely check that one out. And then everybody's favorite topic is tips and tricks, which we're planning on doing something in November for our final Milwaukee Tableau user group meeting of the year. We're going to cover tips and tricks in November. So you can register for all those events now using the link that I just posted in the chat.
Great. Thank you, Brandy.
Thanks, Olga.
And with that, we will have our giveaway. Thanks to everyone that was active in the chat. And Josh, I'll give it to you.
Sure. And again, just to run everybody through. So everybody who made a comment, I logged your name down. Anybody who asked a specific question, kudos to you. You got another log of your name down. So now I'm going to use a random number generator, and we're going to find out which 5 of you are going to walk away with some swag. So let me just get the first one out here. And looks like Mary Workman. So congratulations to you, and Brandy, I'll get you the specific details over to you on that one, but I'll log that these are the winners. Next one is Krista Olson. Congratulations, Krista. And so in this order, you will be able to choose. So Mary Workman first, Krista Olson second, which of these you would like. So we've got the $50 certificates and then the 3 swag packages, and Brandy will have the details on the three swag packages. So I'm assuming the first 2 will probably going to take the $50 gift certificate. So, but if that doesn't sort of happen, then that's kind of how it'll go. So number 3 is Ginger Castle. Congratulations, Ginger, really active in the chat. That was very nice of you. All right, 4. Phil Fram. Congratulations, Phil. And then last is Jordan Miller. Congratulations to everybody. I'll get the details over to Brandy. She'll be in contact with you for the specifics. And the $250 gift certificates, again, those are probably going to go with the swag packages, a bit more variety, and Brandy will have the details on that. So.
Thank you, Josh. So that concludes our meeting, our Q2 meeting. Thank you so much, everyone. Keep up with what's going on at our events page. Join the group at LinkedIn. Communicate with us through Slack, or give us an email. If you have an idea for a topic or you want to present, that'll be great. Thank you so much to everyone that attended. Thank you, Phil and Justin from AE Business Solutions. I thoroughly enjoyed the conversation, and I'm ready to put some of these questions to test with my business users. So thank you, everyone.